Good morning, everybody. Thank you for joining our second annual, or the Golden Gate Chapter second annual Fall and Technology Summit. We have three outstanding presenters today, and we'll be talking about preventative network maintenance, a very topic that's dear to yours truly, because I was involved in it more than 4 decades. So lots of time in that field. With that, I just wanted to touch on some of the SCT benefits. And if you're not a member, you should consider joining, since I met 2 of the 3 people that are discussing today, that will be presenting today through SCTE. And I have to say, my network connections were built out over many years at SCTE. So that's a huge advantage if you want to meet people that know something about our business and can share all that knowledge with you. So that's my plug, and I'll move over to introductions. So first up, we have Jason Rupe. So Jason received his PhD modeling large-scale systems and network performance and reliability. He was a senior technical staff and director at US West/Quest. He's a member of the IEEE. He was a former manager editor of IEEE transactions on reliability, former co-chair for the blockchain initiative, past general chair for the ICPHM, IEEE Reliability Society treasurer, and IEEE chair for ICC 2024. That's a lot of work, Jason. Yeah. He is now a distinguished technologies working on proactive network maintenance, network system service reliability, optical operations and modeling, and DOCSIS 4.0 tools and readiness. I get to serve on that committee with Jason, and he's a lot of fun to work with. So some of the discussion points he will talk about is how P&M lowers operation costs, improving the business case overall, how if even inefficient, and this is important, how inefficient P&M can be better overall than reactive maintenance. So everybody should listen up to that, right? You don't have to be 100% efficiency to do a good job. So payback models must include customer retention and satisfaction, which is fueled by well-maintained networks feeding reliable services. So we're going to move on. So Jason, wave your hand so everybody knows which one you are. Next, we have Brady Volpe. I've known Brady for quite a few years too. So he's the Chief Product Officer at OpenVault, brings over 30 years experience in the broadband and cable and telecommunications industry. He's the founder of Volpe Firm and Nimble, that's now OpenVault. He has been instrumental in product development and successful launches. Through his blog, podcast, and live stream, he shares expertise in high-speed data, DOCSIS, P&M, HFC, ML, PMA, and more. He was the first to commercially introduce P&M, which has revolutionized network optimization in the industry with an unwavering commitment to broadband innovation and advancements in broadband technology. So Brady, that's Brady. And last but not least, missed the discussion point. So Brady's going to be discussing benefits we are already realizing from machine learning, because that's already in play and we're already utilizing it, impairment identification, outage prediction, and PMA, and how technicians will benefit from the use of AI. Larry Wolcott. So Larry is an engineering fellow at Comcast in the Next Generation Access Networks in Denver, Colorado. Larry is a founding member of CableLabs Proactive Network Maintenance Working Group. He serves as chairman of the SCTE Network Operations Subcommittee, Working Group 7, P&M. He's a Comcast ambassador at SCTE and president of the Rocky Mountain, and previous president to the Rocky Mountain chapter. Larry was named SCTE Member of the Year in 2018. He has numerous patents and publications directly related to P&M and cable operations technology. So you can see we have a big We have a lot of great presenters today, and I'm not going to delay it anymore because I'm sure we're a little bit squeezed for time, but I'm sure we have a lot of great information. So I'm going to hand this off to, oh, it's already handed off. I'm going to go on mute, close my screen, and I'm going to let Jason. So Jason, thank you so much for presenting today. We really appreciate your support of our chapter.
Very good. Thanks for having me. Happy to be here and with this very prestigious panel that we have here today to talk about P&M. I'm hoping I set things up for success for everyone else and kind of get everyone's thinking in kind of the right frame for this discussion. I'm going to talk about a very focused topic. It's really about the financial benefits of proactive and preventative maintenance. So when making that distinction, that means we'll talk a little bit about the difference there, but there's a lot of similarities and a very strong relationship. And it's totally fine if you want to kind of use one or the other, but there is a subtle difference there, which can be important. So we'll cover that, and we'll talk a lot about the financial benefits. You won't see a dollar sign in any of this, but you will see some numbers, and the numbers can be thought of in some cases as sort of generic dollars, if you will. So we'll avoid getting into the specifics of how much and how many and things like that, because we're going to run a whole lot of scenarios and show some results there. But to get started, we're going to just kind of talk about some simple concepts. I think when we get through the simple concepts, everybody will have a core set of arguments, if you will, to have a conversation with your peers about why it makes the most sense to really be proactive focused, that it really is a smart choice in general. Looking at just these basic scenarios, I think you can really see clearly that none of the extra stuff that I'm going to show is really all that necessary, but it really does put the exclamation point at the end of the sentence, if you will. So let's start with some concepts. Maintenance, of course, you can look at maintenance in a number of ways. And if you look at the research out there, and we're talking academic research and such, there's probably, depending on how you slice and dice the area, there's thousands, but there could be 100,000 papers out there looking at various types of maintenance, optimizing it, improving it, so on and so forth. Many, many years ago, I did some more academic focused research around that, and I did a count of papers back then, and it was thousands. Decades later, it hasn't waned, it hasn't reduced, because there is so much work to do around making sure that maintenance is done properly and correctly. And so lots and lots of work has progressed, and we are all here as a testament to P&M and proactive network maintenance, as it is, being something that occupies a lot of our time. There is a lot of work that needs to be done going forward, but we've done a lot of work and we continue to make improvements. But let's just talk about the different types of maintenance first. Reactive, that just really means that the service has already failed, that the customer is already feeling an impact and it's severe enough that we'll call it failed. Customer knows something's wrong. Proactive allows us to get in front of that. And so if we've got a system like that blue diamond you see below there, a very fragile system, things are either working or they failed. There is no degradation involved. If something fails in that system, the overall system fails and the service has failed. That's a very fragile system, and that's where you pretty much only can do reactive maintenance. But we're in systems like DOCSIS and telecommunications. All those allow proactive and predictive maintenance to happen. And that happens when you are expanding the difference between working and failed. You introduce resiliency. You've got all sorts of states and all sorts of time to adjust and do the maintenance out there to keep service running without an impact. I mean, service could be really managed in many cases to near perfection. The only kind of failures that really you can't work around is when you don't have a protection switch, you don't have an alternative path, and you have a cut in your connection, which is really more rare these days than anything else. So with proactive, you know that a fault will lead to a failure eventually, and the impact is noticeable now, but it may not be noticeable yet to the service, to the customer, but it's going to happen at some point because there is some sort of impact to service, and it's something that you have an opportunity to address. The difference with predictive is we have the failure there, and we know that it's going to be impacted at some particular point. So we are predicting the point at which that impact will be will turn into a reactive, if you will. So it's sort of like predicting the difference between it's proactive now, but if we wait to this point here, it's going to be reactive. It's going to be something we need to address. It's also going to be something we can apply to, say, a component in the system. While you might have a network with protection switching on your optical backbone, you could look at that optical node there and know that the laser on there is starting to fail, and you can actually work out the math and build a model that will predict with a high degree of certainty when that will fail. You can schedule the maintenance to bring the system down and bring up a new plug-in and a new laser to keep things going without impact. You can even switch over to Protect Link. So that's really what we're talking about in general in maintenance. I'll say a little bit more about it at the end, but right now we're going to dive into proactive network maintenance. And I want to bring you through a few scenarios. These scenarios, we're not going to do much math on these. We're just kind of going to go through these and talk about these, because I think having the right vocabulary and the right thinking here is really mostly of what we want to have as a good foundation for saying we really need to make sure that PNM is the focus. So we'll talk about unstable example, a degrading example. That's degradation in the system. I'm not going to degrade anybody. And a stable example. We're not going to the horse stables. We're talking about an example where we have an impairment in the system and it isn't changing over time. And then we're going to get into talk a little bit about planned maintenance examples and grouping maintenance and where there's an advantage. And then we'll get into some real details. Talking first about the unstable example. This is where we have reactive maintenance. If that's our mantra and we wait until there's a problem, the impairment, it's coming and going. We may even know about it, but we wait until a customer calls in a problem. The technician troubleshoots, doesn't see the problem because it's gone. It's no longer there. They close the ticket. The impairment comes back. Customer calls again. Now very upset. You may have even sent the technician out there. They may have even looked out there and said, well, I can do this and maybe things will get better. And then they leave and you have a repeat. In any case, this is kind of the reactive situation with a lot of these impairments and problems that come and go, which is very typical. But in a proactive world, the impairment comes and you can have it can come and go, but you can have some sort of adjustment to it. Apologies for that. We have a PNM tool that sees that there's an impairment problem. It can help to classify that in usually an automated way by looking at the type of impairment. We can understand it's coming and going, and we can look at it when it comes and say and classify it. That helps us to localize it as well. Continuous data collection to further diagnose. We reference SCTE 280 that tells us what to do in these situations. Technician looks for the problem and the network goes to where the problem is, finds and fixes it. Now that's ideal. It isn't always that way, but it certainly is more that way when you're using your tools fully and you're thinking proactively. In the degrading example, the network is degrading. We see a problem. It is getting worse over time. It's subtle at first, but it gets worse. And then the customer sees the service degrade, but they don't complain at first. Eventually the service is so bad that the customer calls and complains, and they're very upset now because they've been suffering for a while and they know it's a network problem. They just decided the service is so bad, maybe they'll even go to a competitor rather than even deal with it. It's been going on for a while now. But in a proactive world, the impairment is subtle, but it's detected. The impairment gets worse, but not too bad. And the PNM tools help to identify and localize the problem and tell you that it's time to act. And then the technician gets dispatched to the location, instructed to the fix, customer never sees the problem, and service is maintained. And the customer continues to be delighted in that situation. So all is good in there. In a stable example, so this is a case where we have an impairment in the network. It's probably introduced by, it might be pretty severe in some cases, but it's probably introduced by network activity. So there was maybe a repair done where a section of the cable was spliced in, and as a result, those splices were a little imperfect. And now you have an impedance mismatch in two places, creating an echo tunnel, for example. You could have other issues out there, like maybe something that was not quite seated well on a faceplate on a tap, and that could have introduced problems as well. But in a lot of cases, these are the types of problems you can detect, and they don't seem to change over time. There doesn't seem to, at least at first, be any degradation, but it's a detectable problem. Sometimes they're pretty significant, but they're stable, so they get left in many cases. Eventually, a second impairment appears. Now service is impacted because you had a network that already had an impairment. While stable, the network was actually not quite as resilient as it could have been. So now the second impairment comes in there with the earlier impairment compounding it, things have gotten worse. And so now the customer complains, they're unhappy, technician is dispatched urgently, fixing one problem and maybe leaving the network in that low performance state because they may not have fixed the stable problem that was there. So the network stands ready to impact customers again at the next impairment, and that's not where you want to be. Proactive network maintenance, focusing on these impairments, if it's severe enough, will tell you this is something you'll want to address. The network activity introduces a stable but severe impairment. The P&M tools classify it and it indicates it's severe. Proactive technician dispatched to correct the problem. Eventually a second impairment appears, but it doesn't impact service now because the network is now more robust. You have more signal, more ability to carry the signal. A second impairment comes in. It's now another proactive opportunity. The customer remains happy. The second impairment gets corrected opportunistically, no urgency needed, and everyone maintains the network in a very proactive way, and service continues to be very good. All right, so those are just kind of the simple examples. Now let's talk about the proactive advantages. So planned maintenance, that's one of them. So the fact that you can do proactive maintenance means you can plan around it, which means if you can plan it, you can reduce your cost. You can align it to the resources. If you happen to have the ability to schedule technicians, you can schedule a few more on a particular day to do the proactive work. You can make adjustments to schedules. Technicians can take the time off when they need to, and you can plan the work so that when they come in the next day, the work is ready for them and they can still be ahead of the impact for the customers. You can manage overtime down. You can have the best conditions ready. So if it happens to be a real unfortunate day to be doing repairs in a particular area, you can plan for that to be on a more fortunate day. So everything can be planned and ready, and that's a significant advantage, not only to the technicians, but in terms of overall costs. Fix the problem when the customers are impacted least as well. So you can look at the schedule in the area and know that if people are working from home, you don't want to disrupt them during the work hours. You want to, if it's a type of a problem that is going to disrupt service, you can schedule that. You can make sure that nobody is impacted or that the impact is minimized. It also allows you to fix problems when operations are most able to do so. So you have all those planned maintenance advantages. Likewise, you can group maintenance in P&M. Oops, sorry about that. So you can group maintenance in P&M. So you can roll one truck efficiently, which means if you happen to be able to look at your proactive situations, you're not in a reactive mode, you're not chasing problems across the network, you're not driving trucks back and forth, trying to get to them in an urgent way. You can schedule them and you can do what's called the traveling salesman problem, and you can optimize the truck roll, meaning that you can minimize the amount of travel time, the amount of windshield time, and therefore optimize the amount of time that the technician is actually addressing problems. That allows the overall cost of maintenance to be lower, and that increases the amount of time you're actually addressing the problems, which of course is what we all want. And you can also optimize the resources. You got classical traveling salesman problem, as I said, but a lot of advantages come from scheduling and grouping. So that should be a grouping, so apologies for the misspelling there. All right, so that's just kind of the basics here. This, I want to talk a little bit about the concepts here that, you know, the customer is a mystery, and we're all actively trying to address service assurance. Now, there's this concept of service that we all understand pretty well, but there's also the customer use of that service, and that's something we have to think about, because the customer, again, is a bit of a mystery. Sometimes they use them in a way that we would understand. Sometimes they use services a little bit differently. We don't have full control over when and how they use the services we've got. We don't control their mood even, and if they're in an emergency situation, they could be very sensitive to less than optimal service. So we want to think about these as transactions. So a customer is going to use the services in individual transactions. Over time, these transactions build up an experience that gives a customer a sense of what that overall use is like and what they say is good about the service or bad about it. You can think of terms of service level agreements. For some of your more sophisticated customers, you may actually offer a service level agreement, or you may have an internal target that is a very hard target and say, we want to be above this limit. And that's just like a service level agreement. You might be managing just fine to that, but then you get net utility and the impression that the customer has on the service isn't necessarily aligned to that. So we have to be aware of the overall utility that a customer senses from that too. Fortunately, SCT has a working group working on exactly that problem right now, and that's NOS Working Group 8. So if you have interest in going down that path, which highly links the maintenance that you do to the overall customer experience, there's a place for that. All right, so next topic here. Now we get into some weeds here. So I'm going to explain this funny picture you're looking at here a little bit, and then we're going to look at the results of how we exercise this picture. This is a model. It's a stochastic model. So you can think of residing in one of these many, many states, each circle being a state, and each arrow saying how you can move from those states. In the center, you have these kind of orange-red states. That is the network condition. It's working. It's fully working with zero degradation in the far left. And each one of those numbers is a state where you have increasing degradation in the network. I can continue to have impairments happen or damage to the network happen. Each time there is damage to the network, it is a reactive opportunity or a proactive opportunity. So first, we can look at this in a very proactive way. And when the network is perfect, we really don't have a proactive opportunity. The network's perfect. When something happens, we can react to it. So we would just go out and address it. Now, of course, that's still proactive network maintenance if it doesn't impact the customer, but I'm going to call that a reaction to whatever we see. If we want to do fully reactive maintenance, we're going to push that degradation clear to the right on this diagram, because I'm going to go clear out there and just let the degradation happen and not address it. And so if I look at this and just say, I'm going to wait until it's a reactive problem, I'm probably not going to address things, and I'm going to continue to degrade and go to the right and probably not see it. So while I do have arrows going down for each of these states into the reactive mode, that only happens if I'm really looking closely at things and I'm going to be hypersensitive. So most of the time, I'm going to have a proactive situation in those. And so this is going to go clear to the right into clear, heavy degradation of the network. But I'm going to model all states of this network. This allows me to do a few things: understand whether or not there's any advantages to degradation in the network, any cost advantages to doing more proactive versus reactive. So I can kind of control the throttle, if you will, and say, I'm going to push this to go all proactive, or I'm going to push it to go all reactive, or I'm going to have some mix in between. So this model can fully exercise and look at all those scenarios. So that's actually what we're going to do next, and we're going to look at some results like that. So let's look at running a whole bunch of these states, and then let's look at the network as it's around state, what I'll call 38, and that's degradation state 38. So if in that diagram that I had just shown, we had those kind of reddish orange in the middle. So this takes us clear out to about 38 out of 100. You know, if I push it to 100, the network gets really degraded. 38 seemed to be a pretty happy medium, and I'm just going to say, well, look at 38 because it was fairly representative. So you'll see most of the middle states of the network where there's a little bit of degradation, which we all are going to have in our networks, that we're just managing that and we're staying on top of it pretty well. But all those cases where things get a little worse or a little better, the results here that I'm going to show here are mostly the same. Now let's look at a mix of proactive and reactive, which is that bar on the far left. Now we're going to have reactive, and we're going to allow you know, we've got this mix of proactive and reactive. And when we got half the proactive work, but we've got maybe a little bit of success here, but sometimes you know, about half the time we're kind of wasting our time. That's that second one. And that means that I'm doing some proactive work and I'm doing my reactive work, but let's just say my proactive work, I'm not really good at it. I'm batting about half of them. So about half are pretty good. So that means half of them, I'm kind of wasting my time. I'm rolling a truck, I'm going out there, I'm looking for a problem, and I don't really see anything, so I'm not going to get anything done, right? That seems very wasteful. But what this diagram here shows you that in a network, when it's around those middle states, which is what all our networks are, a reactive only situation is going to have very low availability. So it's going to be up there toward the low end there, and my availability is actually going to be much lower when I've got these kind of mixed situations where I'm just doing reactive and I'm being unsuccessful and only doing a little bit of proactive work. Whereas if I've got proactive and reactive together, I have a much higher performing network. Also, if I can look at the overall costs here, If I have a nice mix of proactive and reactive, I have very low cost rate. Now this is a cost rate, this is a cost over time, and it's funny money again, so no dollar signs here. So I've just put in parameters in here that are representative and relational costs into the model and running it a whole bunch and getting a lot of data points here. And what this says is that in all the situations where I do proactive and reactive, I'm pretty good. Now, if I'm just doing reactive stuff and I have a certain amount of repeats where I don't have much opportunity for proactive and I'm not successful on some of my proactive stuff, the end result is I actually have much higher costs. So this is a reactive only approach, trying to say I'm only going to roll when I absolutely need to. You actually see in all those cases, even if you do it perfectly, which is clear at the right end there, you're actually spending a lot of time. You're spending actually a lot more money than doing proactive. You can actually be much more efficient with your proactive work than you can with reactive only. In this proactive scenarios I have here, I exercise this with a whole lot of reasonable parameters, meaning if I can do a little bit of planning, I can maybe reduce some of the truck roll time. But even if I don't do that pretty well, things look still much better overall. There's some cases where there's overlap. So I see here a little bit of overlap up in here and here, but not a lot. It is by far, if you're just gonna set and forget and not really worry about the details too much, proactive reactive is the best way to go. You're gonna have a good mix. Here's some differences between reactive only case to the reactive plus proactive case for all the degradation levels. And you see even here when my network is highly performing, brand new, perfect network, still doing a little bit of proactive, still makes sense. You're not wasting any money by doing proactive at all in even a perfect sense. And as you go out there toward a network that degrades more and more to the right here, boy, you're going to save yourself a ton of money if you do proactive maintenance. It's just going to be much more efficient to be smart with your time. And here's a few scenarios there that tell a very similar story. This is against the cost rate difference between the scenarios. Now we'll look at the highest repeat rate cause to the lowest cost overall repeat case. So looking at all these cases, no matter what your repeats are, if you have a high repeat rate, you're still going to want to be proactive. You're still going to be in a situation where being proactive is going to save you money, even if you become very efficient with your proactive work. So that's the message. Now, what about predictive maintenance? So we're kind of in the home stretch of this first presentation here, but I want to say some about predictive maintenance. So predicting is kind of that predicting the time to failure in the future. There's a lot of value in doing that in some situations. Degradation can be predictable, and this is prognostics and health management. So that's PHM, and if you're interested in that, you can go to phmconf.org and see a conference that happens where we kind of develop the state of the art around this part of the science and predicting those outcomes. But fortunately, with all this work, you can really get to optimal replacement. It's very possible. But how long can you wait? That's really the question there. And in many cases, that's maybe not the best thing to do. In some cases it is, like if you're going to look at network lasers, as I mentioned before, a lot of times they fail to a log normal distribution. You can track the efficiency of those lasers and say at this point here, they will be inefficient, and I can predict the time at which that will happen, so I know how much time I have to react to it. But in a proactive situation, you don't always have that fine level of detail, and I would argue that in many cases you really don't need it either. You're going to save yourself a little bit of time by waiting, but as long as you're doing your schedule and being smart about when you make that decision, you're going to make the right choice. So there's components versus systems that you can think about. Resiliency assures that component failure doesn't lead to a system failure. So you can look at those components, and if you want to get into the prediction game, you can do very well with that. But that's a lot more effort than just being proactive, knowing that it's there, it's smart to do it, I know where to go, I know how to do it, and I can optimize my resources to do it anytime. So schedule and get it done, that's the best choice. DOCSIS is a highly resilient situation, so we can use PNM to assure that service is met. In many situations, performance suffers, so we have to watch it carefully. So that's, kind of a situation there. That's kind of a situation there that's a little bit different, because performance can suffer, but we also have to watch that carefully and make sure that PNM doesn't lead to a service impact. So we can look at that situation and say, how much leeway do I have in my resiliency my resiliency mechanisms? And that's actually work that we're doing in the PNM working groups now to get that to a finer degree. That allows you to at least understand the risk. While you're not necessarily predicting the maintenance, you understand the risk of not addressing it immediately. And that gives you some sense as to how much time you have in order to address it. That gives you some sense to say, how much do I want to wait for that perfect day? This is where PNM becomes PHM in a sense. We can very accurately predict the time of the service may be impacted and replaced before that time, but sometimes it's not so accurate. That's where PNM is best. But remember, service failure can be intermittent. That makes it very hard to be accurate with prediction. So take advantage of DOCSIS resiliency, and as we like to say, use PNM to a fault. With that, you can ask us questions. You can stay up to date with CableLabs. And that's all I have to talk about today.
Thank you, Jason. And I don't see any questions in the question box, but just a reminder, everybody, that we do have a question box that you can type your questions into. I'll be glad to read them out, but just have a comment about some of the things that Jason said. You know, I think when I started like 40 years ago, we were probably 90% reactive and 10% preventative. And I think when I left, we were just the opposite of that. We were probably 90% preventative and 10% reactive. And so thanks to Jason and all the great work of all of our leaders who help us get that turned around, because I think most of the technicians back then, we kind of knew that there was a big benefit to proactive maintenance. But unfortunately, I don't think our voices carried very far at that time. But as you can see, it is, you know, very financially viable to do proactive maintenance and very proactive, very beneficial. So if you were thinking it wasn't, you saw by Jason's slide that it really is.
And if anybody's on that journey and you want some support in trying to move that needle, just reach out to any of us. But I'm certainly interested in helping out with specifics. We can help build some models. We've done that with some operators, help them build some models specifically to their situation so they can build the arguments and help to move that needle.
And that link looks like an excellent link for budgeting. So you can look at, you know, what's coming up next, right? What do I need to do to keep my network running very well? So that is excellent too. So anybody with any questions, Larry or Brady, do you have a question you'd like to ask Jason? We have a couple of minutes.
I don't have a question, but Jason, I think it was a great presentation. You really brought up some really good points that we see from our users that are using PNM, that you know, being reactive and proactive is really a difficult thing to do. So many operators, I think, use PNM reactively, which really brings us into that predictive space that you start to talk about, Jason. So I think that, and the definitions that you brought forward, I think were really helpful for operators to understand: are we reactive, are we proactive, or are we predictive, and or a combination of all of those. So I think that's really helpful.
Common vocabulary. Well said, Brady. And you know, you got to start somewhere, right? And if your tools, if you start with tools that are only supporting reactive work and you're reacting all the time, you don't have visibility into proactive opportunities, you'll never get ahead. And so that's where things like Brady's tools and ours at Comcast, that's all built in, and it's just normal for us, which I love. But great point, both you guys. I'm so excited to be here with you, you two. Some of my
and the argument
friends
to start with, I think is very sound, which is if you see there's a problem out there and you're wondering whether or not you should take that proactive opportunity, don't wait too long to wonder, because eventually it'll be a reactive one.
Yeah, and some of the success stories that I hear often that I don't think we think about all the time is, if you can see that you have a piece of buried trunk cable that goes under a highway, or a trunk cable that's going over a major intersection, it's not like you can just run out and replace that without pulling permits and dealing with a lot of red tape that has to go along with that. So having that visibility to say, we're going to have to replace that trunk cable, and it's going to take us a month or two to pull all the permits. That is a luxury, to know that you have to do it, but people are not down. Modems are not offline. If that trunk cable goes, you know, there's corrosion in or whatever, now it's completely gone, and now you're in a rush scenario. That's a completely different situation. So I get a lot of feedback from cable operators that say this this saves us such aggravation and such rush jobs because we can plan for this. We can get the permits, we can talk to all the city officials, everything, that's all done. And then this is not a fire anymore. This is planned activity. We can do it at a nice day, and all that is manageable.
Great example. Woody, you're on mute.
I still haven't seen a question, so we'll go ahead and just hand it off to Brady. I think I'm ready to do this. Let's see, make presenter. I think you should have the, I think you should be presenter now. Are you not?
Not yet, Woody.
List.
Let's see if I can request it.
Make presenter.
No, I was denied.
Jason may need to do it. Jason, you want to try to make Brady the presenter?
I don't seem to have that level of control, unfortunately.
I do. I'm doing the drop down. Make presenter.
Yeah, and I no longer can present even. So even if I had your slides, I couldn't show them.
Let me go off camera.
Shows you as presenter, Jason.
Volpe connect to mute. Stop web. Make presenter.
Please stand by, ladies and gentlemen, while we're having technical difficulties. Ah, there we go. It just came up.
I just found something embedded in there, so my apologies. It was hidden underneath some menu item, and I just was clicking around, and I think that's what it was.
Okay, I think we're ready to go. Thank you, Brady. Thank you, Jason.
Okay, let me see if I can get it up now. PowerPoint, and my presentation should be visible. If not, please let me know. I'll go ahead and get started. So thanks everyone for joining in today. Thanks to Golden Gate chapter for inviting me to present. My topic today is largely focused on AI. I'll talk a little bit about machine learning, basically how I see it, how my company being network maintenance and mainly proactive network maintenance. I saw something bounce here. Hold on, please. Not right.
Still show you as presenter.
Okay, yeah, no, I got a pop up from GoToMeeting here. I think everyone can still hear me.
Yes, we can see your slide.
Excellent. All right, so yeah, so we'll talk about AI, machine learning, and how it's going to change things. But the real focus here is on AI and what it is. And we've been talking for years. Companies have been talking for years about how AI has been in their products, but really it's primarily been machine learning. But AI has been around for so long. I looked at movies and stuff. So where did AI come into our culture? And 1968 was the first movie. Well, actually, it was a book. The movie itself didn't come out later, but actually, no. This movie did come out in 1968. Arthur C. Clarke's 2001: A Space Odyssey came out long before the movie did. But if anyone I'm sure some of you who are listening are familiar with 2001: Space Odyssey. You saw HAL 6000 that was in it, but that was, this was like kind of the first concept of a completely aware robot or a computer that could talk to Dave. In 2001: A Space Odyssey, it was kind of a spooky, creepy robot in more ways than one, but it was kind of like that concept of a computer that was aware. And then I think the most notable movie after that was The Terminator in 1984. Actually, I was shocked when I looked at the date that The Terminator came out. I couldn't believe it was that long ago. And now I'm really dating myself because some of you are saying 1984. I wasn't even born then. But these were kind of like movies that have sort of shaped our perception of what artificial intelligence is, and maybe where it can go. And we'll get on to that later on. But AI today is really quite different than what we saw in the HAL 6000 and in the Terminator. What AI today is what we're seeing with a company called OpenAI that in June 2002 released a product called ChatGPT. And even ChatGPT in the last year and a half has come a really, really long way, even to the point now where, as you can see on the left-hand side here, I typed in to ChatGPT, I said, generate an image that represents ChatGPT. And on the right-hand side, ChatGPT generated this image, and it said, here's an image that represents ChatGPT, visualizing the concept as a futuristic digital brain with interconnected nodes and networks glowing with energy. The letters GPT are prominently featured in the design, symbolizing the AI's core. We can see the letters GPT. So this is where we are with the state of AI today. You can just ask the AI engine, what we call a large language model, to generate an image of what it thinks it is, and it'll generate an image and it'll describe that image. So we're not quite HAL 6000 or the Terminator yet, but we are at a point where we can communicate with this AI image or this AI engine and ask it, what do you think you look like? And it'll describe that to you. And this gets into something, is this thing alive? Can it pass something we call the Turing test? And the Turing test was something developed by Alan Turing, who was a British mathematician, logician. He was into decrypting things. He was a computer scientist. He was a very talented individual. And he was considered the father of theoretical computer scientists and artificial intelligence and AI. This was back in the 1950s. The purpose of the Turing test proposed by Alan Turing was designed to provide basically a criteria to determine if a machine was capable of thinking or exhibiting intelligence that were indistinguishable from that of a human. And right now, ChatGPT is able to pass the Turing test. It's able to say, basically have conversations with humans that are indistinguishable between whether or not ChatGPT is a human or not. You can't tell the difference, with one exception, is that OpenAI always has ChatGPT remind you that it is a large language model. So that is the one caveat. That's the one thing that always makes ChatGPT make you realize that it's not a human. It continuously reminds you that it's an OpenAI model, or it's a large language model. So that is the thing in our basically our world today, or in science, that is keeping people from saying that ChatGPT is actually not capable of passing the Turing test. It has not reached human intelligence yet, because when you ask it, it will tell you it's not a human. So where do we go from here? If you ask ChatGPT like what it is, what the technology behind it, it tells you that it is artificial intelligence. It's a model developed by OpenAI. OpenAI is the company behind it. It's trained on many, many, many documents. It's trained on the internet. Basically anything out there, it gets trained on. And this is why it's called a large language model, because it's trained on massive amounts of documentation. The model out there today, if you don't pay for the service, you get GPT version 3.5. If you pay for the service, you get GPT version 4, which gives you a lot more capabilities. And all this text on the page here, I actually asked ChatGPT, I said, please give me a couple of paragraphs to explain what you are. So all the text on this page was written 100% by ChatGPT. I cannot take credit for it. And the training for ChatGPT ends in April 2023, which basically means that they just, OpenAI scrubbed the internet for everything, and all of its data ends in April 2023, which tends to be a limitation of these large language models. You cannot get recent data. So if I wanted to know something that happened, as of November 2023, I would actually have to have the model go out and search the internet for current events. So how does that help us in the cable industry, specifically in things like PNM and full band capture? So a technician in the field may be presented with an image that looks like something on the screen today. And this is a full band capture image that we would get. We call this FBC. So DOCSIS 3, most DOCSIS 3.0 and all DOCSIS 3.1 cable modems are capable of receiving all RF signals that arrive at the input of that cable modem inside subscribers' homes. So it's like having a spectrum analyzer in every subscriber's home that gives us the ability to receive those signals. And then once we receive those signals, we can determine if the signals going into subscribers' homes are healthy or if they're impaired. What we're looking at the screen here is a full band capture signal looking at all the signals going into a single subscriber's home, and there are some impairments. Now, we're using existing CableLabs technology called SID, Spectral Impairment Detection, and it's labeling. It's already identifying some impairments. It's telling there's a standing wave on here, so there's sort of a sinusoidal pattern. There's some adjacencies. Standing up here is another impairment on here. And we can do this doing two different methods. There's an algorithm method that we use that SID is based on, and then there's also a way that we can do this using machine learning. Then we can take this further with machine learning. We can look at multiple subscribers' cable modems that may be seeing the same downstream impairment. And we can cluster those together and we can say, okay, we have an outside plant impairment. Let's not roll trucks to individual subscribers' homes. Let's go to the, maybe there's an RF amplifier that's causing this, and that amplifier has some grounding issues. So that would, that helps save truck rolls. Going back to like Jason's presentation, is we want to be proactive and predictive about how we do this. So we don't want to send technicians to individual subscribers' home if we know there's a bad amplifier in the outside plant that would be causing this. So machine learning is really good at this, but what machine learning is not good at doing, or at least the current technology we have, is training our technicians. So we know there's an opportunity here potentially with these AI models to help train our technicians. So we could ask our AI model, and as I said, there was a standing wave in that. We could say, well, what is a standing wave? And if we just ask that in this example in the ChatGPT, what's a standing wave? ChatGPT would say, well, a standing wave is a wave pattern that results from the interference of two waves of the same frequency and amplitude traveling in opposite directions. This phenomenon is common in physics and can be observed in various mediums like strings, air columns, or electromagnetic fields. Well, that response was phenomenally useless. And so one of the reasons the response, and I hear this a lot of times from people that are using tools like ChatGPT or any type of large language models, they say, well, I asked it a question, but the response that I got back was absolutely useless. And it's because we didn't ask it a good question. This falls into something that we call prompt engineering. Good data, bad data in, you get bad data out. So if you don't ask a good question, you're not going to get a good response. So we find out, I'm going to ask this question a little differently this time. And this is something called prompt engineering. And we'll find this with not just ChatGPT, but with all large language models. So if I say, I have a standing wave, remember before I just said, what's a standing wave? Now I'm going to say, I have a standing wave displayed in a full band capture FBC display. What are the possible causes of a standing wave? So, I didn't really go into much more detail, but I ask a more concise question. I have a standing wave. Remember last time I just said I have a standing wave, but now I'm including this standing wave is in a full band capture display. And then I'm saying, what are the possible causes of this? Now, I actually, if I was doing this properly, and I really wanted to expand on this prompt, I would go into, I would include things like, in NCTA papers, I may mention some authors, I may mention CableLabs and SCTE. I'd really expand on this prompt, but I haven't done that. I just made the prompt a little bit more detailed. I expanded on my question. Now, by adding just a little bit more detail, to the prompt. If you remember our other response that ChatGPT gave us, talking about physics and air columns and things that just didn't really apply to the cable TV industry. Now ChatGPT is coming back about my standing wave, and it's telling me, well, I could have an impedance mismatch. I could have connector issues. I could have damaged or faulty cables. I could have issues with splitter or amplifier problems. I could have incorrect cable lengths, frequency response issues, environmental factors, and then it goes into about how I could diagnose these issues. I would typically start by inspecting the physical components like cables and connectors, and then move on to checking the networking equipment like splitters and amplifiers. It's also important to ensure that network design is appropriate for the signal frequencies and power levels being used. Advanced diagnostics using network analyzers and other tools can help pinpoint the exact cause of the standing waves. And if I examine the actual text that is in this, that is repeated, some of these sentences are taken directly from a document that Jason mentioned in his presentation that's called SCTE 280 2022, Understanding and Troubleshooting Cable RF Spectrum. And for those of you who are really, really interested in understanding how to interpret that full band capture picture, I would strongly encourage you to actually download this document called Understanding and Troubleshooting Cable RF Spectrum, which you can get from SCTE's website. Here's the actual URL for it. I also made a bit.ly short link where you can go to https bit.ly/SCTE280, or you can just snap this little QR code, hold your phone up to it and snap it right now while I'm parked on it, and that'll take you directly to the SCTE's website, and you can download this paper absolutely for free. Strongly recommend it. It's going to tell you how to identify, how to understand and troubleshoot all of the types of impairments that you're going to see in full band capture. Impairments like suckouts, standing waves, roll-off, tilt, resonant peaks, adjacencies, all of those type things are in this document. It's an absolutely fantastic document, and I would strongly recommend it. So back to these large language models. A lot of people are concerned that, they're going to kill our jobs. They're going to take away the jobs that we're doing right now, like how to understand and interpret standing waves in full band capture. But this is not the first time, as a culture, we've been concerned about some type of new technology coming in and killing our jobs. We were worried about it in the Industrial Revolution, that machines were going to come and take away all the manual labor, that we were going to do that. With the assembly line, we were worried that we were going to lose all of our manufacturing jobs because the assembly line was going to pump out cars very quickly. The computer revolution, we were worried that computers were going to put a lot of people out of work. Robotics and automation, even the internet, and this, a lot of us will probably remember even when the internet was coming along, concerns about how all that automation was going to put away a lot of jobs that were coming out. But with each one of these technologies, they did remove some jobs, but they opened up an entirely new job opportunity. So they created jobs as well as they just changed the jobs that we have. And we really think that that same thing is going to happen with artificial intelligence. Yes, some jobs will be changed or eliminated, but new jobs will open up, like prompt engineering. The way that we interact with artificial intelligence will change. So it can augment jobs, but some jobs will go away. So AI can help identify where plant impairments are, but AI is not going to be climbing poles and digging ditches and replacing amplifiers or replacing drop cables. There's still going to be things that happen there that AI just simply cannot go and do. Then there's the concept or the concern about the singularity. So we talked about Terminator, and I think that's probably the biggest concern that folks have with AI is just going to take over the world. And I think we've had that same concern. We have fire, the atomic bomb. I think the next slide I go into that. So we have kind of a, so both of these slides are AI generated. This one down here with the Terminator and this one up here with the boomers and doomers. So I think it was just recently, I think it was either the Wall Street Journal or one of the large media outlets came out and said there's basically two types of people right now in AI. There's boomers and doomers. Boomers are people who are like, yeah, AI is going to help us and move things forward, and doomers are like, AI is going to crush the world. So you can probably think to yourself, like maybe which side of the fence you're on that, and then we kind of think how we manage that. So the technology needs to be regulated and controlled without a question. And we've done that with other technologies throughout our history. And I listed a couple of examples in addition to AI. I mean, fire, we discovered fire, we harnessed it, we learned to cook with it, we learned to heat our houses with it at the same time. We have to deal with fire when it's burning our house down or burning forest fires. So fire can definitely be very helpful for us or very dangerous for us. Atomic energy is the same way. We use radiation for X-rays, and at the same time, radiation expanded well beyond what we ever thought it would be to the atomic bomb. At the same time, we use nuclear energy for good and the atomic bomb for bad. We have to manage that, and I think now we're at a point in history where the atomic bomb is really quite concerning, but we're doing our best to manage it. AI, I think it's equally as dangerous as all the other technologies that we have in our arsenal. We talk about taking a pause with AI, but our enemies will not take a pause. So we really have to look at how, as a world, we're going to control and manage AI. But I think one thing is not going to happen. AI is not going to stop moving forward. It's once Pandora's box is unleashed, it's going to keep moving forward. So where are we with ChatGPT as an industry? Like, why are we not just putting ChatGPT in every product that we have and taking advantage of it? So we actually started to early on as ChatGPT came out. We thought, well, this would be great to put in our P&M products and take advantage of it. And then we quickly realized there were security, copyright, data compliance, all kinds of concerns with it. From a copyright standpoint, as I mentioned, like when I said, what is a standing wave? Some of that information came right out of documents that were written and authored by people that are on this panel right now. So there's a copyright concern there of how does our where is our copyrighted information being used? Is anyone getting, do people know where those papers are going? Then we also have the data ownership concern. So if we take a product that is managed and owned by a company like OpenAI and we integrate it into our products, and then let's say that we integrate that into subscriber information, and we say, okay, what's the problem with a particular subscriber's modem? OpenAI suddenly has access to that data, and we don't necessarily know what OpenAI is doing with that data, or maybe some other company like Google, that we possibly be integrating this data in. Maybe we even, just have a technician that is copying and pasting data into ChatGPT because they're trying, in their best earnest to try to understand how to interpret an issue, how to interpret an impairment. And what they don't necessarily understand is that customer proprietary information that they're copying and pasting into OpenAI is actually going to some place that we don't necessarily know where it's going. So we really want to be aware and concerned and cognizant that anything that we copy and paste or that we would integrate into our applications may go someplace that we don't know where it wants to go. And we could be potentially compromising customer proprietary information or subscriber proprietary information. So we kind of came to a point in our understanding that we have to be really, really careful about where our data goes, how our data is used, and then also like the copyright infringement type aspects. So the solution that we kind of came to as an industry is we have to put a pause on pushing data into these public companies like OpenAI and start to use open source AI models that we can locally host, and we can control that data. We can know what data that we're training it on, and we can make sure that any data we put into our open source AI models doesn't go any place that we don't want it to go. So what does this mean to us? As an industry, we can still use AI, but we can't use public or open, AI models like OpenAI, such as ChatGPT, where we don't know what they're training the data on, we don't know where they're using the data. That becomes problematic to us. So we really believe that that AI is going to be very good at assisting technicians in troubleshooting networks and using it to be sort of like a help desk assistant. But we're going to use an open source model that's hosted locally. We know what the data is going to be trained on, so that if we say, hey, the answers that you're getting, here are all the sources, here are all the authors that have contributed to it. If you want to know where that reference came from, we can provide that reference for you. So every piece of information that model has been trained on, we know where it came from, we can reference that model, and we can give accreditations to all the authors who've been part of that model that we've provided. And then these open source AI models can be securely hosted. Any data that you put in, any subscriber data that has gone in, these are going to be locked down, and we know that they're not going to be used nefariously by any third-party companies. So these models are directly integrated within our applications. And then this means that we can also integrate it not just to P&M, but we could integrate it into Wi-Fi networks, into 5G, and now we can start to really expand our AI models into other networks. So sort of a technology convergence. This is sort of the longer view of where we see AI going. Now, the practical application of AI in a P&M application is going to look something like this. So this is where we're taking it right now, to be really a help desk assistant for technicians. So if you think of a technician coming into a P&M application today, they're coming in right off the street, they may not have a lot of training. And so one of their questions might be is, what is FBC? What is full band capture? They may see that in the application, and they, perhaps they haven't had a training. So they can use this AI help desk to give them on the job, in the field training as they need it. So when we say, what is FBC? We have since we're hosting this, we have the ability to do all the prompt engineering for the technician behind the scenes. That means the technician doesn't have to be that prompt engineering. They don't have to do all that extra stuff that we did at the beginning of this presentation of saying, oh, what is FBC in the context of NCTA technical papers and CableLabs and all that. They can just say, what is FBC? And then we append that in the background. So in this case, the response from our AI help desk would be FBC stands for full band capture, which is a feature used in DOCSIS P&M, proactive network maintenance tools. It enables the cable modem to capture and digitize the entire spectrum available to its receiver, not just the DOCSIS channels. This allows for a more comprehensive and in-depth analysis of network conditions, including noise and interference issues. By taking advantage of built-in capabilities within many modern cable modems, FBC can provide valuable insights into the health of the network and help operators identify potential problems before they impact subscribers. So that response came from one of the NCTA technical papers that this particular large language model, again, this is not ChatGPT, this is a large language model that we're hosting in AWS, and it's only accessible by this P&M application. So this P&M application is trained on NCTA papers that, and we have a list of these NCTA papers which are accessible by the end users so they can go through and look at them. But it's a finite list of NCTA papers which have all come from previous cable tech, SCTE cable tech expos. And that list is finite, so we know what it's listed on. Now, if you were to ask this large language model, who is Shakespeare? Or if you were to ask it, you know, write me a poem by Shakespeare in the voice of William Shakespeare, it's going to say, I'm sorry, but I don't have knowledge on that because we've not trained it on anything other than PNM and DOCSIS related technology. So it can only answer questions specific to that. If you ask it anything else, it's going to come back and say, sorry, but I can't answer those questions. Now, I ask it a number of other questions here. I ask it, what is a standing wave, or what is a standing wave in FBC? What does in-channel frequency response mean? What is roll-off? And in each one of these, it gave a response that is specific to that. I'm not going to read each one of these. I'll just leave these up here just because I'm running out of time here. So what is next? So for us, the AI help desk is just the start. We really wanted to get the AI help desk into the application so that technicians have a place where they can immediately go and ask questions about PNM so they can get answers about PNM, because Brady Volpe does not horizontally scale as quickly as our application AI help desk will. But this is just a journey. The next phase will be to enable technicians to ask questions about cable modems and subscribers and get answers back to what those possible impairments would be, such as what is a problem with modem, and then they can just put the MAC address in for that modem. And since the AI help desk is already tied into our application, it'll be able to go and look at that modem. It'll be able to look at the downstream channel levels for that modem, the downstream MER, RxMER, OFDM powers for that modem, the upstream OFDMA, upstream transmit power for the SC QAMs. It'll be able to look at the spectrum analyzer and see how much noise is on the upstream for that particular modem. So it can really look at all the parameters for that modem. Basically what a technician would do, that would maybe take that technician 10, 15, 20 minutes to do in a manual process, and the technician would have to have that experience. But we're training the AI model to have that experience to go through, know what the pass-fail criteria is for the downstream, the upstream return path noise, and then come back to that technician and just say, hey, did you know that this modem has, you know, bad upstream SNR? And so it gives the technician a starting place. And then we'll just continually evolve that. So ideally, the AI model will be able to come back and say, this modem has XY problem, and we would recommend that you would start looking at this particular line extender. That's the end goal, where we really believe AI will be able to get you to go. So again, AI is not going to be able to fix the plant. It's not going to replace your job as a technician, but where we see AI going is the place where you can just say, here's the subscriber, what's the problem? Is it an in-home problem? Is it an outside problem? Where do I go look, and what should I be looking for? It's there to assist you and also help you gain knowledge along the way and be there as your co-pilot when you're using the applications. So in wrapping things up, AI it's here. It's not going to go away. So whether you're a boomer or a doomer, I really encourage you to start embracing it, because we can't put it back in the box. It's going to bring some really interesting capabilities. It already is. I mean, if you have questions about PNM or DOCSIS or troubleshooting, you can already start asking questions. But remember, the way you ask the question is as important as the question you're asking it itself. The way we're going to be using these large language models is only limited by the way we can think about using it. Like, you know, we're thinking about ways we can use it, but it's limited to our imagination. So if there's new ways that you can think we should be thinking about using AI, please let us know. So it is a new technology, but like the internet, we're going to learn to tame it. I think the questions that I'd be interested in is what are your thoughts? What are your concerns about AI, and how do you see us using it?
I don't see any questions in the chat box, yes, but I guess what you're saying, Brady, is if you ask a broad question, you're going to get a broad answer, right? So if you really want, specific information, you need to ask specific questions, right? Put
Yes.
in as many details as you can before Chad goes out and tries to look those up.
Prompt engineering is key. Yeah. Very clear and concise questions.
Yeah, but I do think, not that I'm not a gloomer hater, but if you look back at those milestones in history, you actually saw booms in employment after each one of those, right? So when the Industrial Revolution, okay, well, we need people to build these things. So, they started hiring people, right? We got to the assembly line. All of a sudden, we can make cars. So people started buying cars. And then they said, wait a second, we can make tractors so we can plant more fields. So, agriculture boomed. And then, we can make planes. So now everybody's flying, right? So yeah, don't be a doomer if you can avoid it, because one technology breakthrough leads to more, and we have more people working now than in any point in history. So I don't see that changing. Let's see, Brady or Larry and Jason, do you have some questions for Brady?
I got one if there's time. Brady, you demonstrated to us that these tools, which I would just sort of put into a big bucket of kind of the present day automation capabilities, because they can help us automate a lot of things. In there, you showed that in the sort of whole chain of maintenance of PNM, we can use these to identify faults in the network, classify them. Maybe eventually we'll get to where it'll help us to localize them as well. And then we can help guide the technician in the repair process. That seems to be a pretty complete chain there. So what's the next step or the next version of automating Brady, Volpe, and Larry Wolcott? What does it help us to do kind of the next level? While it isn't going to replace a technician, is it going to replace the work that we do, that all of us do? Or is it going to help us to kind of look at things a little bit differently and take it to the next level? What is your thought there?
I mean, I think it gives us the ability to take us to the next level, Jason, because a lot of the things that I use ChatGPT for, or large language, I'm starting to use less ChatGPT and more of our own large language model, is to do less of the typical work that I do and more advanced work. And I have a feeling that that's just going to be the continuous theme that we use these large language models. If taking the technician as an example, the technician, rather than having to go outside of an application to Google, they can use a help desk within an application and get the answers, and that will continue to evolve to, rather than having to continuously ask questions, they can just say, what's the problem with this modem? And I think we're just going to see that continuous evolution moving forward, not just for technicians, but for all of us in the field.
The way I think about it, maybe this isn't necessarily philosophical, but the way I kind of think about it, which seems to be in line with your thinking, is that these almost serve as mirrors to us, in that we can look and say, what do we know? And in that fact, in that ability, we can identify what we don't know. And that kind of helps us to identify the work that we need to focus on next. It helps us understand our gaps in our knowledge, where we need to work next. And that's that high level work that I think that we can take to the next level. So I'm with you on this. I think it helps us improve our game. It's not going to replace us, because there's so much more work to do. But maybe eventually we'll get to a point where we can do other things entirely. Who knows? It's a step at a time. We're going to keep climbing that ladder.
Love that. So I do have a comment for you, not so much a question, but I'll just throw a softball over the plate. So we're all, I'll just say it, we're all co-authors on that SCTE 280 paper, and I talk it up in my little bit here too coming up. And one of the things you don't really think about is, so the machines are out there scraping this information and transforming it into things that are sometimes more useful than we are at writing, which is great. Like, they can translate it to different languages and to different levels of comprehension, and it's really, really beneficial. It's not bad at all. But we're also rethinking about how we actually write the materials and being very deliberate about the pictures that we use that humans are really good at. Some of these LLMs don't have great multimedia capabilities, so they can't interpret the pictures. So we have to, write alt text around the images and videos and do a much more descriptive, textually descriptive job at how we author these papers. And there are certain writing styles that are more effective than others with LLMs as well. So we're really, really taking this serious. And the idea is not to replace humans, it's to make us better. Like, to me, a great analogy is Google Maps, right? You remember the days when we used to print out maps, or we would MapQuest something where you'd print out the directions. Now you don't think twice about using Google Maps, and you don't think anything less of yourself as a driver or a human because you're relying on good directions. Sometimes they're not good. That's part of the game. But to me, assistance and help desk and Copilot for troubleshooting, repairing cable services can be a lot like Google Maps. It's going to be more informative and allow me to focus more on the fun part, which is fixing the cable, than it is finding it and diagnosing it and doing stuff wrong a few times until you figure out what was right. Like, I know that's fun for some people, but really the gratification of fixing stuff effectively is so much better for everyone. So
Great.
You can always
analogy,
use
Larry.
Google Maps.
I love that your presentation, Brady, and Jason too. You guys, we're all birds of a feather here. So.
And correct me if I'm wrong, but you can create you can create a feedback loop. So you can also monitor what people are asking, right? Okay, so where am I not getting through to everybody we're missing
100%. Yeah.
So how many technicians out there?
And what could we do better to help improve the adoption of this stuff, right? Like, that's more, what does the machine keep getting wrong? Why do we keep getting stuck in this one thing? Well, maybe we weren't right about certain things. So it's pretty powerful.
It doesn't replace it, improves.
Yeah.
Okay, I don't see any questions. So I think I saw what was wrong a while ago when I tried to switch presenters. And what was wrong was there was a pop-up and it was buried. I couldn't find it. So let me try this one more time. Let's see, we're going to go to, oh, Larry, you already it. Somebody did ahead of me. Thank you, Brady.
We can't hear Larry now.
Yeah, we lost your audio.
Oh boy, clicking some stuff like crazy here. Do you hear me now?
Yes.
Yes, we do.
Okay. Now we're having some technical difficulties. Yay, it looks like we're full screen. Is it, everybody confirm that?
We are full screen.
Awesome.
Yep.
I'm going to do a time check here because you know me, I love this and I can go forever. We have 25 minutes. I'm Larry Wolcott. I'm a Comcast fellow and I've been in the operations technology space. My new gig is technically called Field Operations Research and Development, although that's basically what I've been doing for the last 18 years here, 17. PNM, I'll give you a very quick background. We've already talked about this a bunch. One of the founding members, as you heard earlier, with the PNM working group at CableLabs. Jason came in later, but boy, I tell you, we are so happy to have him and his vast years of experience coming in from DSL of all things. I just spilled the beans on you, Jason. Brady was right there with me on the formation of PNM, along with a bunch of other really talented, brilliant folks in this industry. And we also have this working group 7 in SCTE. We decided just to be more effective with our resources and our time is to allow the different working groups to focus on CableLabs working group is more of the science and the technology and the algorithms, and working group 7 is more of the art. This is where the rubber hits the road and we translate really complex things into simple but effective guidance for technicians and all of this stuff. So that's why we're here in SCTE talking about working group 7. The efforts of this group are focused on standardizing and expediting new PNM technology to operations in the field. That's how do we make this really complicated thing simple and effective for the field to use so that we don't have to spend a whole bunch of time getting PhDs. All right, so the PNM journey, this is interesting for those of you who know me. I remember Woody invited me out to California when we just started this stuff years ago, almost 15 years ago, not quite, 13, 14 years ago. And we talked about Scout Flux. This is our very first PNM tool. It was based on adaptive pre-equalizers. Well, we have co-opted a whole bunch of really great technology, and now P&M really is any tool that we can use to help proactively identify problems before and even sometimes after customers are impacted. It's basically our operations tool stack. Pre-EQ, that's our what we would at Comcast call flux and other stuff. Full band capture, this is SCTE 280. We'll talk a little bit about that. Upstream diagnostic analyzer, this is new. RX MER, FEC statistics, PMA, profile management. Upstream triggered spectrum capture, Yeti, we call it. It's just basically your upstream spectrum analyzer. Maybe you know it as PathTrack in your company. Transmit headroom, we'll talk about that. That's new. We've got a new way of looking at upstream transmitters. Of course, signal levels and link budgets and all of that, and frequency response characterization, AKA formerly known as sweep. Sweep, some people say sweep is dead. I don't try and insult the process, but I do disdain the technology. Anyway, we'll get to that. These are all of the things in our P&M journey. There's a lot. We came from pre-equalizers to a whole bunch of really powerful tools, and also sometimes very complicated, which is where we welcome AI to help. I'm going to talk about the working group 7 output. This is what I chair. Jason is my counterpart at CableLabs, and we kind of collaborate and meet regularly and make sure that our agendas are aligned, and we focus on the art and the science together, which is really a fun way to work and be effective. A couple of the things we're working on right now, the big outputs that we've got, SCTE 280, this is not actually new, except for we're so proud of this thing. Go ahead and next slide talks a little bit more about it. We're working on and done draft mode with upstream version of 280. So 280 is focused on downstream RF. Upstream is where it's at, baby. We're super excited about this. It's in the working group internal peer review right now, and you should see an announcement very soon about being available. So that doesn't have a number yet, but it's probably going to be 287 or something like that. And of course, we're right now updating all of the P&M training material in SCTE, and we're going to do it in a way that's indexable really effectively with AI, so that you don't necessarily have to stare at a screen and take a test. Maybe the next version of the training will be AI assistance. So that's kind of exciting for us for a new frontier. We talked about SCTE 280. I won't lie, I just added this QR code when I saw Brady did this. Good job, Brady. But so anyway, these are our spectral impairments, and every single one of these. There's even more in the book, the Bible of RF impairments. All of these different things. It explains what the mechanisms are that cause them, typical things in the field that we see. What do you do to fix it? How do you verify that it's fixed? Really, really great stuff here. I did not put a bit.ly URL. There's the whole thing. It's a standards document, or you can just Google SCTE 280, or you can click the QR code. Just go get it. It's such a fantastic knowledge base. And by the way, if you go ask ChatGPT with a little bit of correct prompt engineering, it's already going to know all this stuff and tell you the right answer. And as Brady talked about, where you get the information and how you ask the question has everything to do with the quality of the answer you're going to get. I have asked it a whole bunch of questions very loosely with not a lot of guardrails, and it clearly is scraping every piece of junk from Reddit that was ever written from everybody and their mama. And a lot of times it'll tell you to just swap the cable modem and all this other stuff, and that's not at all the right answer. So Brady really covered it well, and I appreciate his attention to that. Yeah, it's all about how you ask the question and where you get the information from that it synthesizes into its response. So make sure you say NCTA, SCTE, CableLabs, give it those clues, and it's going to come back with much better answers than some of the other stuff. This is an example. I love this. So after you've gone and fixed 1 or 2 or 10 or 100 of these things, you're just going to burn that image into your mind. In the upper right-hand corner, that standing wave is an aperiodic high attenuation frequency response. That is only caused by one thing in the universe that we know of yet, and it's water in a coaxial cable. And there's a few things that are kind of similar, but that thing is so unique that there's water in the cable. We've gotten out to cables where they look absolutely perfect except for one tiny little nick or ding in that thing, and nobody would ever swap the cable because it was only 6 months old and it looked perfect. But golly, when you take the thing down and you TDR it, sure enough, it's filled with water. But you never could tell by looking at the cable without actually TDR it. Know that when you see that signature, your cable is soaked with water. Now, would you ever know that without reading SCTE 280? Maybe, but read SCTE 280 and it will give you all the gory details about the physics behind it if you're interested, and everything you need to know. Anyway, just a fascinating example. If you weren't aware of what water in a cable looks like, by the way, our models are trained here at Comcast, and you'll see if you're a Comcast employee, water wave detection, single drop replacement tickets that are already tagged, severity assessments, and you're going to get out there and replace a lot of water soaked cables because this thing is super accurate in the 90s, high 90s percentile. You know, there's other things that can kind of look like it and trick the machines, but mostly it's that good. Very exciting. So our new upstream version of SCTE 280, I am super excited about because we spend more time on the upstream and it causes a lot more difficulty for us than the downstream, I'll just be honest. And it's a lot harder, but it is here and there's a lot more that is coming that you need to know about that you might not know about, including mid-split and high-split and full duplex and how actual power is calculated and all this other stuff that's incredibly important, and you need to get it from somewhere. So I would encourage you to be on the lookout when you see the upstream counterpart and go download that as well. Upstream noise localization, behold the holy grail. Some of you, if you've ever looked in the full band capture of our cable modems, might notice this strange looking power hump, you know, on a subsplit network. It would be up to about 42 megahertz. And that is actually the view of the cable modem's upstream frequency spectrum from the other side of the diplex filter. And that can show you where the noise is getting in, if it happens to be getting in there at the right amplitude and the right timing and all this other stuff. So this is an example. We have a paper that was published just this expo a month or two ago, and it explains how it all works, but know that something really new and really important is coming, and it is the ability to detect, locate, and analyze the sources of upstream noise ingress using this new technology. And so it's super exciting. That's one of the things that's coming out of our PNM working groups. And you can go to NCTE technical papers and just search for UDA, or there's the URL, or Wolcott. There's a bunch of us that contributed to this as well. That's very exciting. Total composite power headroom. This is a little bit of a mind game here, but know that once you turn on mid-splits, additional frequency spectrum, high split, full duplex, you need more power to get more spectrum up there. And as you enable that upstream frequency spectrum, you encounter more challenges and link budget considerations that you might have not thought about, or filters out there in amplifiers or other types of things. And you know, this is an example when you shift the curve 6 dB to the left by adding more need for upstream transmit power, all of a sudden, if you don't have that power, you might end up in situations where you're not able to completely bond. And so we're getting ahead of that. Great work. There's another paper a whole bunch of us contributed to, including calculator. There's a great link for the online calculator here from PromptLink. If you want to plug in your values and see, it's not just, by the way, what's your transmit power and what's the max? There's a whole bunch of complexity in there, but it's fascinating to see, hey, what's the dynamic range window and how much headroom do I have? Do you know that? Well, this will tell you. Dynamic range window, the min channel power. How much power does the adaptive pre-equalizer, how does that factor into the calculation of the total composite power? Well, download the document. It's pretty fascinating. We all learned a lot, even the people who built the chips that do it. We're all surprised at the amount of unexpected complexity and learning that was available to all of us. FM ingress location, I'm doing a time check here. We've got a few minutes left. New ways, if you use the Comcast tools, you know that the dreaded FM ingress is not everywhere, but it's all over the place. And turns out that if we process those signals in a couple of clever ways, we can actually group those together and do a really good job at saying, this is where those particular signals are getting in. Now, oftentimes there's more than one place, and that's where it gets really interesting. But if you, excuse me, have a common cracked cable, for example, and a bunch of people are seeing that same FM ingress, that can be grouped together using different AI techniques. And then you can have one or two of those customers or completely different customers that also have leaks coming in their drops. And those can be separated out and say that these customers are part of the leak caused by this cracked cable. These two customers have leaky drops. And now all of a sudden, we get a lot more operational intelligence, so we can be effective about sending tech ops to go replace drops and network folks to go repair cracks. Really, really big opportunity there. And this is frankly not new. It's been around for about 10 years, but we're just really focused on using it in new ways, especially because AI is so helpful to us. So more to come on FM ingress as a tool to find leaks. Full duplex DOCSIS is here. I don't have a ton of time, but I will play a quick video. Let's see if this works. These 6 downstream OFDM carriers are 108 to 684 megahertz. That's a fully occupied downstream full duplex. And there you see these channels go back, jump up. I'm going to back that up and play that again for you. That's downstream OFDM. Watch right here. Now there's upstream transmissions going at exactly the same time. So you have downstream OFDM and upstream OFDMA playing concurrently with multi-gig services over exactly the same frequency spectrum. And wow, things are just about to get super interesting here in cable land. And then you can see the upstream transmission stop and the power levels go back down to downstream. So very fascinating how it works. It's incredibly valuable because it effectively doubles the potential spectrum we can use, and especially for limited upstream environments. But that creates a bunch of new complexities, and let me show you what that looks like. Okay, you thought your upstream troubleshooting was a little bonkers before. We have one upstream signal now, but we're digitally separating the upstream, the downstream, the echo components, the noise floor. So this is one signal trace that we get from the burst receiver today that has 7 digitally separated components that now allows us to click the buttons and say, show me the upstream, show me the downstream, show me the echoes, show me the ingress, show me the noise floor. All of those are digitally manipulated from the one signal that are received at the receiver. And so the opportunity for us to really improve how this is interpreted and used for troubleshooting, it's not just important, it's mandatory. It's getting so complex that a human can't look at electrons and understand what to do anymore. We have to have much more machine assistance to help answer some of these questions. And this is what our upstream looks like when you have the downstream in it. This is not a fully loaded OFDM downstream, upstream, and a full duplex system, but this is an extended spectrum view at the burst receiver that also shows upstream and downstream. In a full duplex network, you have what I just showed you, OFDM and OFDMA, with different views that allow you to select out the RF components of interest, whether it be upstream or downstream or echoes or whatever, noise flow or ingress. Very, very exciting from a technology perspective, and also a little intimidating because there's a lot of complexity here. But rest assured, the machines are here to help you. I promise you that. It's going to be easier, not harder. Leakage gets very interesting because if you think about the amount of energy we're going to be transmitting from the cable modems is significantly higher in places that we haven't been transmitting before, we're going to start to see leaks coming from the home and drop network where we didn't necessarily see them or care about them as much before. It's kind of an inversion paradigm here, where it used to be the high energy was near the outputs of the amplifiers, now the high energy is coming from the home. Well, it's actually both now, but it's going to get interesting. There are a lot of leaky drops out there. This is in part why we're working on that FM ingress stuff. And there's a lot of cost and complexity when you have to do leakage with your home fulfillment, install and repair technicians that you weren't necessarily focused on before. And so that's why we're working on new technology that are P&M related using OUDP, we have new techniques that allow us to transmit with the cable modem. The leakage signal is actually going to come from the cable modem. Go think about that one for a minute. And as you drive up down a street in a neighborhood, we're going to be timing cable modem chirps or bursts to be just ahead of the truck as it's traveling. No kidding. It's pretty interesting stuff. And because of the specialized waveforms we're transmitting from the cable modems, it's not just a tone, it's a fully coherent waveform that we can actually, as the truck is driving by and we're receiving these things, we can interpret slight compression and elongation of the phase component. And the reason that's important is because that's essentially what Doppler processing gives us, so that you can tell, did I go, am I approaching it or am I going past it? And that's really important because with nifty satellite, or sorry, radar processing technology, there are things called a particle filter that allow you to zero in after you build up enough samples to exactly where the leak is coming from. So here's what that looks like as an animation. This is some pretty bonkers technology. Today is the image on the left. When you go drive up to it, you got a rough magnitude and you say, oh, it's getting stronger. And when you keep drive away, oh, it may be getting weaker, kind of. But with the particle filter, there are directional components built into that, so that as the more you drive around the neighborhood, it further refines the particle density of where it believes the leak is correlated to. And even multiple leaks, you'll start to see multiple dots. So instead of you have a leak in this general area, it will give you a pinpoint with a magnitude that's incredibly precise, so that we'll, although it is pretty daunting to have to go fixing a bunch of drops and all this stuff, we'll have a lot more precise information about where the leaks are and what to do to go fix them. So that's another one of the big things, not necessarily full duplex, but DOCSIS 4.0 related, that's coming out of P&M. And with that, at the end of my presentation, hopefully I didn't overrun. I wasn't watching the clock real well. What did I do on time?
You definitely didn't overrun. I wish we had a few more questions. Let's see. We did have a question earlier from Franca, and her question was, are we moving away from people training people? And I'd have to say, probably absolutely not. But it might, AI and other tools can give us, kind of help us focus on where we need to do training. Obviously, you're not going to train a person how to handle a ladder or drive a truck or core cable or dig a hole, or get call in for a USA locate and all of that stuff. But we can get that feedback from AI and say, hey, this is where we're having problems. Let's focus on getting training on these particular topics. Anybody else like to chime in on that?
Yeah, I'll get a little one in there. And so that in GPT, the T stands for transformation. No, pre-trained transformation model. Yeah, it is transformation. That's where it really is helpful, because it adapts the content to something that it figures out pretty quick is more consumable by me at the level and understanding and language that I use. So transforming, helping humans absorb it better is really, really where the AI is. Now, will it completely replace humans from training? I don't really think so, but I think it will absolutely augment in how we train, and it will definitely be impacted, but I don't think trainers are going to lose their jobs anytime soon.
Every time we apply it, we learn that it doesn't replace, it improves. So we will just find a way to fold it into our processes, learning included, and teaching, so that it plays there as well, and it will make things better.
Yeah, and Larry, I think you made a really good point earlier that I actually wanted to expand on. You talked about the SCTE 280 document and what a great document it is, but getting it out to the people is a challenge, or even getting every technician to sit down and read the document from beginning to end is a great challenge. But having these large language models in the hands of technicians, so they can say, what is a standing wave, and have, because we've created that content that's available to technicians now to give them a good, concise answer. I think that's something that AI brings us that's so powerful that we didn't have before, to just quickly boil down information that we've created. We've curated that information, and now it can, large language models can quickly take a question from a technician, extract that information from a document that we know has been correctly created, and present that back to the technician in a way that makes sense to the technician. Because I think that was something we didn't talk about about AI, is AI can take something very, very technical and replay it or respond to you in a way that it can be toned down. For example, I use it oftentimes where I say, you know, take this paragraph and read it back to me like I'm a sixth grader. And that's extraordinarily helpful if you have something that is really a complex subject. And some of the documents we write can be quite complex. So I think that's a fantastic thing about these AI models as well.
We had a comment from Mark Millett. Some of you guys may have remember Mark when he's with Cisco, but
Mark,
he says light years away from looking at modem ranging power and adjustments. Great job. So he's been out of the industry for a little while, but he does like to peek in and see what's going on occasionally. Thank you for the comment, Mark. Anything else from the audience? Well, I'll take this opportunity to talk about what's going on the rest of the day. So at 10 o'clock local time, we have Taming CPD using data and tools. We have Roman Pershansky. I hope I didn't say that name too wrong. That starts at 10. 1 o'clock, we have plant integrity, hardening the plant for improved performance and reliability, where we'll talk some more about the UDP, right? Because things get very interesting in FDD or FDD in high split. Now we have one thing that we working with Jason, one thing I think Ron brought it up is there's actually aeronauticals up around 700 megahertz, right? So I don't think we looked at that. We didn't even know. So the FCC requirements get even more interesting for leakage. And then at 2 o'clock, we have network preparation for extended spectrum DOCSIS. So for those that can join us, we're going to talk about, you know, what happens when we put those OFDMs out there, you know, above one gigahertz, right? Maybe even in where plant it wasn't designed for above 1 gigahertz. I know at my location here, we originally built the system to 870, but we're using it up to 1 gig. Without very little, no extra work from the network other than getting the remote PHY node and get the amps changed. So we're going to talk a little bit about that. But I'd like to just a special thanks to Larry and Jason and Brady for taking the time to get on here. We have people from across the entire country, from New York to Alaska, down to Music City, and then a few people out of the country. So thank you for joining, because I know some of you are butting up to about midnight right now. So that was great that you were able to join, and we look forward to hopefully seeing you guys somewhere, maybe at the next Cable Tech Expo. And very important, if you're not a member, become a member. You can download the papers we talked about today, and you can read them at your leisure. So thank you, everybody, and I'll talk to you later today.
thanks, Hal.
Cheers.